So now, using the equation we found in the last video, we're going to go back to revisiting the ideal gas equation. So for an ideal monatomic gas, we add an extra assumption on the assumptions we had before, and that's that the internal energy of a gas is due only to its translational kinetic energy. So what does this mean? Well, it means that as before, we've got no attractive intermolecular forces, we've got no internal potential energy. So here, for instance, we had attractive intermolecular forces, we'd have some sort of potential energy associated with it. As we pull them apart, we'd be giving them greater potential energy. So we don't have this. There's no intermolecular forces here. Equally, we can also now ignore any rotational energy of the atoms or the molecules. So the kinetic energy is purely translational. What do we mean by that? It just means that we're ignoring any of this rotational energy as being so much smaller than our kinetic energy that we just don't need to really worry about it. Or indeed, it's physically not possible if we think of them being as entirely point particles. Either way, we ignore the rotational energy as well. So really, we think of an ideal gas really as like just a collection of tiny particles or tiny balls like we've experienced in our previous problems that are only free to translate around and have no forces between them and just collide with each other and bounce off, and that's it. It really is just like having a tiny gas of little balls, whatever, that bounce around, that move at very high speeds, and that's kind of what we see an ideal gas as. No intermolecular forces, and ignoring any of this rotational energy, so we're just thinking of these things translating around. So now, what's the mean kinetic energy of our gas? If we had to write down a formula for our kinetic energy, what would it be? So see, all we have to do is just add all of the individual kinetic energies of our particles. So we've got particles 1, 2, all the way up to n. All we do is we say this is the K of particle 1, 2, particle number n, etc. So that's the total kinetic energy. So now what's the mean kinetic energy of a molecule of gas? So the mean kinetic energy of a molecule of our gas. Before I write that down, I'm just going to refine our answer for our kinetic energy a little further. We realise we can take all of these half m's out the front and just have c1 squared plus c2 squared all the way up to plus cn squared here. And that's a conciser way of writing this. So the mean kinetic energy of a molecule of our gas is just going to be the total kinetic energy divided by our number of molecules, which just means we use the formula above and divide it by n. The formula above is half m times by c1 squared plus c2 squared all the way up to plus cn squared divided by n, the total number of molecules, which we realise is just our root mean square speed squared. So that is just a half mcrms squared. So just to write that out so we can box it, because that's a really important equation, and that tells us why using the CRMS, the root mean square speed, is so important, because this is why it slots in so nicely for the mean kinetic energy of a molecule of gas.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.